Okay, thanks everyone for coming to the ESE PhD student colloquium. Today's speaker is Saad Aleemb, who is undergraduate degree in electrical engineering at Lahore University of Management Sciences in Pakistan, for coming to University of Pennsylvania, where he's been working with Ali Jadbai and George Papas. So without further ado, Saad, the floor is yours.
Thanks, Alec, for the introduction. Hi, my name is Saad, and I'm a ESE PhD student at Penn. And today I would like to present our work on self-regulated pursuit-evasion that I've been doing with Cameron and Dr. George Papas at Department of Electrical Engineering and Electrical and Systems Engineering at Penn. We have been working on this project for the past year or so, so I would like to use this forum to present our main results and get your feedback on the results that we have so far. So without any further ado, let's begin. So I would like to begin with the overview of the problem of pursuit-evasion. The problem of pursuit-evasion has been quite a popular topic, especially in modeling the predator-prey behaviors in nature. And in context of engineering, this problem of pursuit-evasion has been explored quite in depth in the case of combat games, where we have to model a pursuer and the goal is to capture an evasive target. And it has also been studied quite extensively in the case of differential games. More recently, in the case of robotics, pursuit and evasion has been studied in quite a lot of problems. Some of the problems are related to motion planning, especially in the case of in the presence of adversarial agents in closed polygonal environments. So one of the few examples is that the pursuers are trying to isolate a fast enough evasive target in a closed polygonal environment, and they have to plan their motion accordingly. And more recently, some of the problems have a taste of the visibility-based search algorithms, in which the idea is to get a coordinated search and rescue missions going in order to locate a target and get to it as quickly as possible in order to capture it. So this shows that pursuit evasion has been traditionally a very important topic in engineering and still remains an active area of research. So mathematically, what this problem means is that in simple terms, the problem consists of a single pursuer and a single evader, with the target of the pursuer is to catch the evader. So the way we define the capture is that as soon as the agents are within some predefined epsilon radius within each other, we define capture. So it's not like they are instantaneously overlapping with one another spatially. As soon as the agents are within some predefined epsilon radius, we define capture. So we define the position of the pursuer by RP and the position of the evader by RE, and capital R denotes the metric of separation between the agents. So if we're interested in capture of the evader, then we are interested in decreasing separation between the agents over time. So for the purpose of this talk, what we will consider is that we will consider simple dynamics of the agent. So we will restrict the dynamics of the agent to single integrators, where both the agents are bounded by some finite speeds. The speed of the pursuer is given by Vp. The maximum speed of the pursuer is given by Vp, and that of the evader is given by Ve. And for the case where Ve is strictly less than Vp, we know that there is a pursuer strategy that will guarantee capture. So that pursuer strategy is known as classical pursuer strategy, is given by this. So basically what it means is that continuously track the evader at all times and head towards it with your maximum possible speed. So this is a very simple control implementation for the pursuer, in which the pursuer is at all times tracking the evader and heading towards it with maximum possible speed. However, as you can see that the pursuer requires continuous tracking of the evader. So this will require many samples of the evader in order to capture it. So this is inefficient in terms of the sensing requirement on part of the pursuer. It is also sensitive to the uncertainties in sampling the evader, because if you're not detecting the position of the evader correctly, then you are not going to get the right kind of controller updates. And in context of the pursuit evasion problem, this strategy might be too naive, in the sense that the more samples that we are taking, the more exposed we are leaving ourselves to our adversaries. So there's a risk of increased exposure to our adversaries the more samples we are taking in our pursuit strategy. So to conclude, this is a simple control implementation, but wasteful in terms of the resources of tracking and sensing requirement on part of the pursuer. So the question that we are asking right now is, can the pursuer is still able to catch the evader without tracking it at all times? So can we relax this continuous tracking assumption and still be able to catch the evader? So this brings us to the other major part of our work, and that is impressed by the research in the trigger control area. So the idea is that in trigger control, what we are looking for is that we want to trade the communication on part of the agents by increasing the decision making locally on part of the different agents. So what happens is that instead of sampling the system fast enough based on some predetermined heuristic and then coming up with a control strategy and then observing the performance, the trigger control works in a slightly different way, that given a system performance, we come up with a controller design, and the idea is to get the information or to see in the future or pre-compute when is the next instance that the agents need to communicate or sense the state of the system. So instead of sensing the system continuously, periodically with a predetermined heuristic, we get some performance of the system in mind, come up with a controller design, and the idea is to come up with the next instance at which we need to observe the system or get the information from the system in order to preserve that system performance. So why are we interested in trigger control? Because they are aimed at reducing the sensing/tracking requirement on part of the agents. So it improves the bandwidth utilization if we're talking in terms of communication between different agents. And it is also robust to uncertainties, because we can trade that uncertainty in sensing or communication on part of the agents to the autonomous decision-making level of the agents. And after coming to the pursuit-evasion problem, this might be a better way of tracking the evader, because if we're tracking the evader and still be able to capture it with less number of samples, the less exposed we are or the less conspicuous we are in terms of our pursuit strategy. So the conclusion from the trigger control is that it requires increased decision making on part of the agents and is aimed at sporadic or less sensing requirement on part of the whole system. So this work on trigger control has received a lot of attention recently. People have tried to implement this trigger control implementation in the case of network dynamical systems, wireless systems, more recently in the case of optical deployment of different agents, and also in consensus. So the idea is that they have certain system performance in mind. For example, in the case of consensus, the idea is that the agents should converge to the average opinion, the average initial opinion in steady state. But instead of communicating at all times, or the agents communicate in a triggered manner, that they only communicate when they need to. They only share information, or they only receive information from the neighbors when they need to, and are still able to converge to the average initial consensus, average initial opinion of the entire system. So typically, there are two types of triggering mechanism that are found in literature. One is event-triggered. The other is self-triggered. Event-triggered is slightly reactive in a manner. So what is happening is that the agents are somehow keeping track of some certificate or a metric, and as soon as that certificate is satisfied or that metric is violated, they trigger in terms of disseminating the information in the network or receiving the information from the neighbors. The self-triggered is proactive. So it is slightly different from the event-triggered mechanism. And what happens is that based on the current information that the agents have, they pre-compute the next instance autonomously. They pre-compute the next instance at which they need to share information with each other or to sample some state of the system in order to guarantee the system performance. So for the purpose of our work, we will stick with the self-triggered and come up with the autonomous decision-making on part of the pursuer. So all of this work, which once again has received a lot of attention in different kind of settings, hasn't been studied in the case of pursuit and evasion. And being impressed by this trigger control strategy, we would like to apply this kind of framework to the problem of pursuit and evasion. So So far, we have motivated the problem. We have said that pursuit-evasion is an active area of research, and we would like to borrow the tools and the framework from the trigger control area and apply that to the problem of pursuit-evasion. So now what I would like to do is I would like to present the problem statement of the self-triggered pursuit-evasion, and then discuss the steps that how do we go about designing that self-triggered update duration for the pursuer, which will guarantee capture of the evader with infinite time with finite number of evader samples. So just to revisit the classical pursuit strategy, we had that track the evader at all times and head towards it with your maximum speed, and we already know the drawback that you need continuous tracking of the evader. So our objective is to capture the evader without tracking it at all times. So we would like to relax this continuous tracking or sensing requirement on part of the pursuer. So the way we go about it is that what we're basically interested in somehow coming up with this sporadic instances of evader observation such that we evade the evader at certain points in time, and in between our updates we would like to implement the zero order hold of the above classical pursuit strategy. So what is happening in between updates is that based on our last observation of the evader, we are heading towards with our maximum speed. So the idea is that if we can come up with a finite number of samples which will guarantee capture, we will only require sporadic controller updates on part of the pursuer. Because in between updates, the evader observation, we do not need to update our control strategy. So this is our idea. I mean, if we can come up with this, then we are actually achieving our goal. So the way we define our problem is that we would like to find this update duration or the sleep duration in between evader observations. So if we can find that update duration, so basically the pursuer receives information about the evader, and based on the current information about the evader that he has, it can find this sleep duration denoted by phi, which is the function of the current separation between the agents and depends on the maximum speeds of the agents, such that it is able to pre-compute the next instance at which it needs to sample the evader state in order to capture it. Then we can say that our pursuit strategy is self-triggered in that way, and we would like to design the self-triggered duration in a way that will ultimately guarantee capture of the evader. So the way we go about designing is that we first of all normalize the speeds of the agents. So we set the maximum speed of these pursuer to 1, and set the maximum speed of the evader to some constant, some mu, which is strictly less than 1. So we know that there exists a pursuit strategy that will be eventually able to capture the evader. Then the way we go about designing the triggering instance is that at the instance where the separation of the agents can possibly increase. So the way we go about is that suppose at time tk the pursuer observes the evader at the position rek. Then for any time tau greater than or equal to 0, we know that the evader is going to be anywhere inside this ball of radius mu tau, which is centered at the location of the evader. So it's going to be a circle in R2. And what we are interested in is that we would like to find the instance at which the separation of the agents can possibly increase. So mathematically what we can do is we can maximize the derivative of the separation of the agents subject to this reachable set of the evader for tau greater than or equal to 0, and then find the instance, find the first time at which the separation of the agents can possibly increase. That is, the separation can become non-negative. So we trigger at the instance when we know that there exists a evader strategy for which the separation between the agents can possibly increase. This is how we define our self-triggered update duration. Since we have normalized the evader speed to 1, we see that we will see that this self-triggered update duration is a function of the current separation between the agents, or the last observed separation between the agents, and the maximum evader speed given by mu. So for the case of integrated dynamics, we can actually find a closed form analytical function for the self-figured output duration, which is given by this formula. As you can see, this is a function of the last observed separation between the agents and a function of the evaded speed, which is given by this expression. And as you can see that increasing mu, which means that the evaded speed is becoming closer and closer to that of the pursuer, the self-figured output duration is decreasing. So basically, intuitively, it means that the faster the evader is moving, it affords us less update duration between our samples and would require more and more samples in order to capture the evader. So the design of the self-figured output duration was that we were triggering at the instance where we were afraid that the separation between the agents can possibly increase. We can actually go and show that if we follow the self-figured pursue strategy for the pursuer, in which we use the phi that we have derived earlier, we can actually guarantee decreasing separation between the agents between successive updates. So we can show that for the self-figured output duration that we just derived, the new separation between the agents at time tk plus 1 will follow this inequality, that rk plus 1 will be less than or equal to rk times h of mu, where h of mu is a monotonically increasing function in mu, and it is strictly less than 1 for mu to be in the interval 0 and 1. So this shows that the separation between the agents is decreasing between successive updates. So for a predefined capture radius epsilon, we should be able to guarantee the capture of the evader in certain amount of time. So we can actually show that for the nth observation, the current separation between the agents is given by this inequality, and if we can actually go on and somehow sort of get an estimate of the maximum number of samples that we will require in order to capture the evader. So what we can do is we can set this expression r0, where r0 is the initial separation between the agents, h to the power n less than or equal to epsilon, where epsilon is the predefined capture radius, and we can see that the maximum number of samples that we will require in order to capture the evader is given by this formula. And for a predefined positive capture radius, which is less than the initial separation between the agents, this expression is finite. And I don't have a plot here, but for increasing mu, we can show that the maximum number of samples required to capture the evader also increases. So if the evader is moving fast enough, this agrees with our intuition that we will require more samples in order to capture it. But the maximum number of samples still remains finite. It will increase, but it will remain finite. So this shows that there is no Zeno behavior. And what do I mean by that? That in order to guarantee some kind of system performance, in our case the system performance is guaranteed capture of the evader, we do not require infinitely many samples in order to capture it, or in order to guarantee the system performance. So we can, based on this, we can see that we only require finite number of evader observation and still be able to capture it. We can also find the upper bound on the time to capture, and that is given by this expression r0 minus epsilon divided by the difference of the agent speeds. So we get the maximum time to capture in the case when the evader is actively moving away from us, and for all the evader strategies, the actual time to capture is going to be less than that. So to summarize the results so far, what we have is that using the self-figured output duration or the self-figured pursuit strategy, we have guaranteed the capture of the evader using only finite evader observations and in finite time, as opposed to the classical pursuit strategy, which guaranteed the capture in finite time but was continuously tracking the evader at all times. So the main result so far is that we are guaranteed capture of the evader without sacrificing any performance in terms of the maximum time to capture the evader. So let's move on a little bit and use some kind of trade-off and study the trade-off between the number of samples that we require and the actual time to capture. So the idea is that if somehow we can guarantee more decrease between successive updates, we can capture the evader quickly, but probably at the cost of more evader observations. So we would like to somehow mathematically capture that intuition. So the way we go about it is that instead of triggering at the instance where the separation between the agents can possibly increase, that is r dot becomes equal to 0, we would like to trigger at the instance where r dot is given, r dot is equal to minus delta, where delta is some constant. And we set the delta, this is just a design choice that we set delta to be a scaled version of the last observed separation between the agents, where alpha is some positive constant. So the idea is that the alpha is a parameter which is going to capture or reflect the trade-off between the number of samples that we require against the actual time to capture in capturing the evader. So greater the alpha, it will result in more decrease in separation in between successive updates, but the intuition is that it will also require us more samples in order to capture the evader. So we define the parameterized self-figured duration. So instead of triggering at the instance where r dot is equal to 0, now we trigger at the instance where the maximum separation, where the maximum of the derivative is given by minus alpha times rk, where rk is the last observed separation. But we cannot take alpha to be arbitrarily large. As you can see that the domain of alpha is given by this open interval, which is the function of the maximum evader speed, because otherwise if we take alpha to be arbitrarily large, we can possibly violate the positivity constraint or the positivity condition or the self-figured duration. So in order to guarantee that our self-figured duration remains positive, we have to choose alpha within this open interval, which is the function of the maximum evader speed. So just like before, we have shown that increasing alpha allows faster capture of the evader because it will be decreasing the separation between the successive updates by some positive amount, and our intuition is that it will come at a cost of increased evader observations. So for this parameterized self-figured duration, we can again show that the nth observation, at the instance of nth observation, the separation between the agents satisfies this inequality, where again h alpha of mu is a monotonic function in both alpha and mu, and is strictly less than 1 for mu to be in this interval and alpha satisfying its domain. And once again, setting this expression to be less than epsilon, we can find the maximum number of samples as a function of both alpha and the evader speed. So this plot actually shows the intuition that we have. We know that increasing alpha will allow us to capture the evader quickly because it will cause more decrease in separation between successive updates. So you can see from this plot is that for any evader speed, increasing alpha forces more and more samples out of the pursuit strategy. So for any evader speed, you can see that increasing alpha is forcing more samples out of the pursuit strategy in order to capture the evader. And for any fixed alpha, increasing the evader speed also increases the number of samples required to capture the evader, which agreed with our previous intuition about the maximum number of samples and how will they change once we increase the evader speed. So this is an experiment that we ran in order to show the trade-off between the actual time to capture and the number of samples as a function of the parameter alpha, or in terms of the parameter alpha. So remember that we previously had an upper bound on the maximum on the time to capture, and the actual time to capture depends on how exactly is the evader behaving. So we model an evader which is moving directly away from us, but it is restricted to move in one of the 4 directions, or it can move only in 4 directions, that is up, down, right, and left. And we set the capture radius to be r0 divided by 1000. So for this kind of experiment, we see that the self-figured pursuit strategy resulted in, for any evader speed, the actual time to capture was decreasing as we increased alpha, but as we increased alpha for any evader speed, it was forcing more and more samples in order to capture the evader. So for this experiment, actually now agrees with our intuition and with our results so far that using this alpha, we have now parameterized this class of pursuit strategies, a more greedy class of pursuit strategies, which force more samples out of our pursuit strategy at the advantage of decreased time to capture. Okay, to summarize the talk so far, what we have so far is that we have studied the design of self-regardable duration, using which the pursuer is able to cache the evader in finite time with only finite number of observations. And I went about going over the design, that what is the triggering instance in designing that self-regardable duration. Now I would like to move to the point that this self-regardable duration, this framework of self-regard analysis, is actually robust to uncertainty in sensing the evader. And what do I mean by that is that we can actually take care of uncertain observations. So previously what we had, that whenever we were observing the evader, we were observing it precisely. We had perfect information where the evader is. Practically this is not possible. We will always have some kind of error associated with our observation. So what we can do is we can actually, using this framework, we can actually put this computation or put this uncertainty in the autonomous decision making on part of the pursuer. So we would like to consider the case where the information about the evader is not precise and it is uncertain, and we will actually show that the self-regard framework is robust in a manner that it allows us to capture this uncertainty in the decision making, or the autonomous decision making part of the evader's design. So what we'll do is, for each measurement, the pursuer measures the evader state or the evader position with an associated error of gamma k. And again, we just as a design choice, we can make this uncertainty as a scaled version of the current observed separation between the agents. And the reason for using gamma k as a scaled version of the current observed separation between the agents is that beta, again now gamma k, using gamma k as beta times rk, beta will be able to reflect the amount of uncertainty that we can tolerate while preserving the same self-regard pursuit strategy. So beta is just like alpha was a parameter which was sort of capturing the trade-off between the number of samples and the actual time to capture. Now beta will be a parameter which will be sort of again capturing the number of samples against the maximum allowable uncertainty in capturing the evader. So we use the same framework that we were using before. Previously, whenever we observed the evader, our reachable set was starting from a point. Now, since we have an associated uncertainty of gamma k in our observations, the reachable set of the evader is now going to start from a ball of gamma k. So it will not start from a point, it will start from a ball of gamma k. So basically it means that we are uncertain about our true position of the evader. The true position of the evader is initially located inside this green ball of gamma k, and for tau greater than or equal to 0, the reachable set of the evader is given by the black ball, which has the radius of mu tau plus gamma k and is centered at the evader observation at RE hat. So once again, we will like to maximize the derivative separation over this reachable set and try to find the self-regardable duration. And like before, we have a closed form expression for the self-regardable duration, which is a function of beta and the evader speed. And the thing is that, again, once again, to guarantee the positivity of the self-regardable duration, we cannot pick beta to be arbitrarily large, which means that we cannot accommodate arbitrarily large uncertainty in sampling the evader state. So once again, beta belongs to this open interval, which is a function of the evader speed, and this plot actually shows that this plot actually captures the intuition. So if the evader is moving slowly, we can tolerate, or we are allowed to tolerate more error in sampling the evader state. So you can see that when the evader speed is small, we have a greater range of beta that we can play with. And for any fixed evader speed, increasing beta, that is, if we allow more uncertainty in our observations, we are afforded less in terms of the self-regardable duration. So increasing beta for any evader speed decreases the self-regardable duration. So this means that if we increase beta, which means that we are allowing more and more uncertainty in our evader observation, we will be required to sample the evader state more frequently as the upper duration is going to now possibly decrease. So once again, like before, we can show that at the instance of nth update, the separation between the agents is satisfy this inequality. This times h beta times h beta of v times to the power raised to the power n, and setting this expression to be less than or equal to the epsilon, where epsilon is the predefined capture radius, we can once again find a formula for the maximum number of samples as a function of beta and mu, which will guarantee capture of the evader and for a predefined capture radius which is positive and less than r naught, this again expression is finite. So this plot shows the graph between the number of samples, the maximum number of samples against the parameter beta for various evader speeds. So again, once again, for any evader speed, increasing beta forces more and more samples out of the self-repeated pursuit strategy. And once again, if the evader is moving slowly, we can allow for greater uncertainty in tracking the evader. All right. Now, so what we have done so far is, now I would like to mention a case that we can actually counter this uncertainty in sensing the evader in a slightly design by slightly modifying the design also. So what we have done so far is that we only rely on the current observation of the evader and set up the reachable set of the evader based on the current observation, and then try to find the self-repeated duration based on that. So the idea is that, and my claim is that, in the case of uncertainty, we can actually do slightly better. And if we can somehow retain the memory or retain the past knowledge about the evader also. So to motivate that, let us see that why did we need memoryless in the case of in the absence of uncertainty, and why we might be interested in the case of memory over self-repeated pursuit strategy in the case of uncertainty. So in the absence of uncertainty, remember that suppose at time tk minus 1, we observed the evader, found the self-repeated duration, and then we knew that after that time, after the self-repeated duration, the reachable set of the evader is given by this dotted black line, and our new evader sample at time tk, that is at rek, will be inside this ball. So which means that for any time greater than or equal to 0, the current reachable set of the current observation will be given by this red ball, and the current reachable set of the previous estimate of the evader will be given by the black ball. So it would have also increased by the amount mu tau. So this shows that the current reachable set is a subset of the previous reachable set, or the current reachable set of the previous estimate. So therefore, we can discard the previous estimate of the evader, and we only need to keep track of the current sample of the evader state. This was when we were sampling the evader state perfectly without any uncertainty. However, in the case of uncertainty, this is no longer true. So once again, with the introduction of uncertainty, what we can have is that we sample the state of the evader at time tk minus 1 at rek minus 1 and find the self-repeated duration. And after that duration, we again sample the evader state. I think it's not clear here, but somewhere inside this reachable set. But we are now uncertain about our evader position. So basically, the true position of the evader is given by this green ball, and you can see that this does not completely lie within the reachable set of the previous estimate. And therefore, for time greater than or equal to 0, once both of these balls are going to expand, you can see that the reachable set of the evader is going to lie at the intersection of these balls, which are not necessarily, so this is not necessarily going to completely lie within the reachable set of the previous estimate. So basically, in terms of optimization, what is happening is that in the case of uncertainty, by incorporating the previous estimate of the evader, we can potentially reduce the current reachable set or the feasible set of the evader, and that can help us in getting potentially longer sleep durations. So increasing or retaining the history will increase the decision making on part of the pursuer, but the advantage of that is that we can utilize this memory or utilize this previous estimate to come up with slightly longer sleep durations in our pursuit strategy. So I would like to highlight one thing is, so we were able to come up with these nice analytical functions in the case of memory-less pursuit strategy. But in memory-aware strategy, what will happen is that we might not be able to do so. So what will happen is that, so previously what we had was we were trying to maximize the separation of the derivative subject to the current reachable set of the evader based on the current estimate. Now what we will do is that in memory-aware, suppose we have the capability of tracking keeping track of m previous estimates, we make our problem a bit more constrained. So basically, we are potentially reducing the possible reachable set of the evader by introducing the reachable sets of the m previous evader observations. So the B e j tau is nothing but the current reachable set of the jth previous evader observation, and I is the set of the redundant previous estimates. We can discard those estimates which happen to give us no additional information. For example, if the current observation or the instance at the instance of current sample of the evader, if the ball of the current if the current reachable set of the evader happens to completely lie in one of the previous estimates, then we can discard that index. So we do not necessarily have to completely keep track of the m previous estimates. We can discard those estimates which are redundant for us. But the idea is that by keeping track of previous estimates, we can potentially improve the self-figured duration. And what do I mean by improve? Is that we can allow for longer sleep durations in between our pursuit strategy while still guaranteeing capture. So this is a numerical result which sort of explains the advantage of retaining history. So we once again set up the experiment like before, and we are now keeping track of only the last observed evader position on top of the current observation of the evader, and we are measuring the evader with an uncertainty of gamma is equal to 0.1 at the instance of each observation. So if we use the memoryless or the memory aware, we will get different update durations, and that will mean that the separation between the agents at the instance of new update is going to change. So basically, what I mean to say is that it is probably not a fair comparison to compare the memoryless self-figured update duration against the memory aware self-figured update duration directly. Probably a better comparison would be to normalize these self-figured update durations, and by dividing them with the current observed separation between the agents. So basically, if we normalize the memoryless self-figured update duration and the memory aware self-figured update duration by only keeping track of one previous estimate, you can see that in the case of memory aware, we are allowed slightly longer sleep durations as opposed to the memoryless case. So the take-home message is that retaining last estimate improves the current sleep duration of the pursuer. Okay, so to summarize the results, so in this talk I presented the self-figured pursuit evasion, in which we designed the self-figured pursuit strategy for the pursuer. We came up with the self-figured update duration for the pursuer, which guaranteed the capture of the evader in finite time with finite number of samples. The pursuit strategy is actually independent of the evader strategy. It only requires to know that what is the maximum evader speed, because it then constructs the ball or the reachable set based on that. It doesn't actually need to know what exactly or how exactly is the evader actually moving. It guarantees the capture without sacrificing any performance in terms of the maximum time to capture. It allows us to trade faster capture of the evader at the cost of increased number of samples or more number of samples in order to capture the evader. It is robust to uncertainty because we can take care of the uncertainty in the autonomous decision making on part of the pursuer, and then we can leverage the information about the evader's past in improving the self-triggered arbitration while still preserving the self-triggered pursuit strategy for the evader. And moving forward, right now we are working towards implementing a team-triggered strategy for the pursuer. So the idea is to extend these results to the case of multiple pursuers. There exists a result in the literature that if the evader is restricted in the convex hull of the multiple pursuers, then there exist strategies that will guarantee capture of the evader. So now we are looking towards team-triggered strategies for the multi-agent system, such that not only we are keeping track of the evader in a triggered manner, but we are also communicating or sharing information with other agents also in a triggered manner, not continuously, but also in a triggered manner. So this concludes the presentation, and now I would like to know the feedback of you guys of our work so far. Okay.
I have a question about the decision-making strategy.
Okay.
As far as I've understood, the agent needs to compute R dots, right, to decide the sampling time.
Yes. Yes.
And R dots, I think, it also depends on the evader's speed.
Yeah, the maximum speed of the evader. Yes. So we had
So we need to have access to both the position and the velocity of the evader, right?
So not exactly. What we can do is that for the single integrated dynamics, in which we can upper bound the velocity of the evader, in R dot we only need to have access to what the velocity of the dynamics of the pursuer are, and we can actually come up with a more conservative estimate of the R dot by just bounding it with the evader speed. So to follow with that, I mean, we don't need to know exactly with what speed what is the exact velocity of the speed instantaneously. We upper bound it. So it is a more conservative estimate, but it allows us to forget what the evader is doing actually.
Yeah, for question regarding the plot, the showing of maximum velocity versus the time interval of sampling. I think it's slide number 11.
Okay. Yeah.
So intuitively speaking, if the maximum velocity of the evasion is 0, then
Yes.
you just need one sample since it stays there forever. But from this plot, you still have this one sample per second.
No, this is actually normalized. I've divided it by the current separation. I'm just plotting it the function of the evader speed. I'm plotting it the normalized upward duration, not the exact upward duration, the normalized upward duration. The upward duration depends on the current separation between the agents and the evader speed. So this plot is just to show that what is the impact of the speed on the normalized upward duration. It is not exactly the the 1 second for that matter.
Yeah, right. But if the evader is far from you, then
Yes.
you still need one samples, which is proportional to the distance.
Yeah, but we do not know that. So this is the idea. I mean, we do not know for sure that the evader is going to remain stationary at all times.
Okay, thank you.
Your result for 2D only, or
For a 2D only, in R2, yes.
it can be extended? Or?
Yeah, if we, so right now we are, so the extension would be to, make it in R3, but I think a more important extension would be to make more complicated dynamics in a way that right now we have single integrated dynamics. So maybe so this allows us to change the position of the agents instantaneously. So maybe we can introduce some kind of theta dot that so that the agents are not able to move or change their position instantaneously. So that would again increase the dimension of the system, but the dynamics will still remain in R2, but the state of the system will increase to 3 in that regard. So that is one possible extension of the work also, that relax this instantaneous change in direction of the agents.
Yeah, so there's a big connection between, apparently between the thing that you've done and sampling of signals in frequency. So if you see the speed of the evader as the maximum frequency, it's like sampling of a band-limited signal, right?
Yes.
So, and you're using a zero-order
Hold of the, yes.
Yeah. So I think that that extension that you said about improving on the dynamics of the evader would be, I mean, restrictions on this sampling that could improve, maybe if you improve the interpolation of things like that. I think, have you considered doing that? Because that sounds like awesome. That sounds like a really good idea.
Yeah, so right now, I mean, what we are doing right now was to extend this framework, like stick with the same number of, same kind of dynamics for the case of the multiple agent systems. Because we felt that maybe because this concept of trigger control makes more sense when we are also communicating and sharing information with our neighbors also. So right now we're working on that, but again, yes, this is, like you mentioned, this is a very, theoretically, this is a very useful direction that we would like to explore.
When you plot the number of samples versus alpha, in the slide maybe 15 or 16, the y-axis was logarithmic, but it is still exponentially fast, so maybe n is increasing w exponentially in alpha. So in practice, you can only have alpha at a very low value, otherwise n would explode very fast.
Yeah, so but the alpha is, wait, I have it. So yeah, alpha cannot be, so actually yes, if alpha pushes this value, you can actually show that n explodes. And therefore alpha is to be strictly less than this maximum speed of the evader. I mean, then we will have zero behavior. We will need to sample the evader set infinitely often in order to capture it.
Okay, but even if alpha is strictly less than that value, still the evolution of n and max versus alpha is probably exponentially fast. So still alpha should.
Yeah, so I agree that the trade-off in that regard is that maybe we are decreasing, we incur very. So yeah, increasing alpha, yes, allows us to capture the evader quickly, but at the cost of, yes, much more samples. Yes, this is true. From these are actual simulations, so you are right actually, that increasing alpha increases the actual number of samples. But this is, by the way, the maximum number of samples needed to guarantee the capture. This is again a conservative, this is an upper bound on the number of samples that we will require. In practice, we might require less number of samples, because the actual number of samples depends on how exactly is the evader moving.
One more question: when you are considering uncertainty and the way you address uncertainty, what's the advantage to just decreasing r hat, right? Like considering the worst case and then decreasing r hat by the amount of uncertainty.
Decreasing r hat?
R hat of k.
So decreasing r hat by why do we need to decrease it then?
Decrease it.
So that will again, yeah, I mean that is again, how do I go about this? Yes, if we increase the r hat by that uncertain amount, but that uncertainty can be, I mean, it can potentially be decreasing separation between the agents also, right? So again, that will be a conservative upper bound, what you're just saying, that we always increase the r hat by that amount uncertainty, whatever we have, right? But it can, so this framework actually caters both the situation in which the actual separation the true separation between the agents might also be less than what we have observed. So this is slightly better than that in that case. What you are saying will give us a more conservative, less sleep duration between successive updates. So using this framework, we might get better estimates also.
In terms of number of samples that you need to take, will you give less samples as well?
I'm not so sure about that. Probably the same number of samples. Yeah, I'm not so sure about that. Once again, this graph is between the maximum number of samples. This is an upper bound on the number of samples that will guarantee capture. This is not the actual number of samples.
Yes. So let's thank the speaker one more time.